late because I was in office hours. So test number 3, it's going to be online. And suppose I have to figure this out, but it will be about momentum and torque. So we have to decide of a date. It's going to be in the evening. I will open a window of like 3 hours, so plenty of time. So don't miss it, right? It will be online on Canvas at home, and it won't have as much weight. It's going to have like, forgot, check the syllabus. Less than test 1 and test 2, but you should be able to boost your grade with test number 3. So it's more like an online assignment. But don't miss it, because if you miss it, you will have to take it in person in my office. Okay? So coming up, I have to figure this out. We have to finish the unit about momentum. So if you missed the last class, I hope that you did catch up. And of course, you all have a textbook, and of course, you want to open your textbook and study. So we did that. That's going to be for the pop quiz today. So pop quiz, I have to leave at 3:40, okay? Because I have to vote. I didn't vote yet. So that's on my to-do list. Yeah. Why, there was a good line?
Yeah, it's like shoulder to shoulder. It's got conga line, basically.
Ah. Okay, 26. Okay, I think we did this one, right? So I just want to review very quickly. So conservation of momentum, it's quite easy. Okay, it's easier than what we have been doing so far. But you do have to remember that velocity is a vector. So you have to decide which way is plus, which way is minus. So velocity can be negative. So conservation of momentum comes from the fact that you have a Newton's third law. For every action, you have an equal and opposite reaction. You cannot push harder than you're being pushed, and you can not push harder than you are being pushing. Okay, so conservation of momentum before, that's the momentum before, equals momentum after, the total momentum after. And the only thing that you have to remember is to pay attention to the sign. Okay, so we already did this one. We did this one, right? 26, number 1. Okay, so let's do it quickly, but we did it. But just quickly, just a review. So how do we want to solve those kinds of problems? First thing you have to draw. So first thing you have to decide which way is plus, which way is minus. Second thing, you have a full back. I have no idea what it is, but it's quite heavy. 100 kilograms is quite heavy, and it's going west. So I'm going to do 3.5 meter per second west. Okay, and then it's colliding with a defensive back. So I guess it's someone who is trying to defend whatever it's defending, and it's moving at 6 meters, so much quicker. So you're going to have something like this for the pop quiz. If you want to know which one is going to win, you multiply 100 by 3.5. That will be the total momentum of this one. That will be 350. 350, am I right? Okay, so the momentum before here is 350. Okay, we did that already. And the momentum of this one will be 4. Very good. Okay. And yes, you're right. So moving to the left, so it will be minus 480. You have to be careful. This one is moving to the left. Agree? Mm-hmm. But pop quiz of today, which one will be winning? That will be this one. Even though he has less mass, because he's going so fast, and so he's gonna win. I mean, they're gonna move to the left together. So they collide together, they stick to each other, right? 80 and 100, and they're gonna be moving this way, V1 prime. And it should not be So they're going to move this way. Okay, so we did that last time. Do you agree? And so the total momentum before, which is 350 minus 480, will be equals to the total momentum after. So it's going to be worse for this guy because it's bouncing off. So for the brain, this is very bad. This one is just slowing down. Okay, so how we do that? We're going to do 300 times 3.5, and here we want to minus because it's moving to the left. So 6 times 80, but we did that already, equals, now it's like one big blob. So it will be 180 times v prime. And you want to make sure to have v prime should be negative. Okay, well, we already did that, and we found. Did we find 4.6, something like this? 0.7, 0.72 v prime equals minus, no, minus 0.72. Do you all agree? We did that last time, so it's just a review. So just very much pay attention to the sign. If it's moving to the left, the velocity is negative, so that means you will have to subtract. If you do the total momentum before, which is what? 130? No, negative. Negative what? How much is that? 480 minus 350. 130 kilogram meter per second. So that's the total momentum before. And the total momentum after is also equals to minus 130. This is just a consequence that even though they are not going to experience the same acceleration, the force will be the same because you cannot push without being pushed. Okay, the consequence is not the same for this one. This one will experience more acceleration because not only it's going to stop and then it's going to reverse the motion. So it's bouncing. Bouncing is more acceleration. Agree? Okay. Okay, and number 2, we did it also. So this is a situation always in the final. I like this one. Ice skater is a classic. It's a classic. You always like, you find that it's a recoil situation. Okay, so it's recoil situation. It means before no one is moving. I don't know, one is 80. The other one is 30. And they push each other and it's not moving. And they push each other, and then here is an example of a demo that you can do. You can go to the ice rink in Miami. It's 32. So this one is gonna recoil, and this one is gonna recoil, but this one has more velocity because it has more mass. Okay, you can call, I forgot, right? You need to call this one number 1. You always have a thing number 1, thing number 2. Dr. Seuss, number 1, number 2, right? So you can say before nothing is moving, after M1V1 prime plus M2V2 prime. And if you want to get a shortcut, you have this equation here. So whatever the ratio is between the mass is going to be the same ratio between the speed. So the larger here is going to be 3. So this one will be more. How much more? So thing number 1, we say 32. Thing number 2 is 80 minus 3 over 3, 7.5. 7, no, minus 7.5, right? Okay, so that will be a magic equation that you want to use for recoil situation. typical two ice skater and or a gun or a cannon or something like this, right? Or slingshot. Okay, so it's quite simple. This it's a relief, right? It's much easier than kinematics, much easier than equilibrium. What about number 5? Did we do it? No. Okay, let's do quickly. Go for it. Make a drawing. The first thing, you always make a drawing. So first thing you decide, okay, I can put plus here, minus, da, da, da. Okay, so before, you do before. Okay, don't wait for me, okay? Just do the drawing. Okay, so this one is moving and it says 12 meters per second. This one is not moving, 18,000. It says, okay, I'm going to call that thing number 1, thing number 2. After, obviously, this one will be the winner because it has the largest momentum. Whatever has the largest momentum wins. And this one is going to move back. Okay? Okay. Question 1. What is the initial momentum of the first car? Yeah. So do you all agree? It's going to be mass of thing 1 times the velocity of thing 1, right? Do you all agree? So it's going to be 12,000 times 12. So momentum is 144,000 kilogram meter per second. Okay? And that will be also the total momentum before. What is the velocity of the two cars once they clump together? They are glued together? Huh? Yeah. Wait, everyone. So before equals after, right? So before you have 144,000 equals after, it's going to be M1 V prime plus M2 V prime. Do you see they move together? So V1 prime equals V2 prime equals V prime. Do you all agree? Right? They move together. Okay? We did that last time. And so you have 144. So momentum before equals M1. So that will be 12,000 V prime plus 18,000 V prime. So that's going to be 144,000. And then you combine like terms. So 12,000 potatoes plus 18,000 potatoes. That's going to be 30,000 potatoes. V prime. Agree? Okay. And you go by. V prime equals 144 over 30, which is 4.80 rate. Any question? Right? It's easy. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Any question? You know, I'm partially blind, so everything is very fuzzy, so I don't see what expression you have on your face. I don't know if you understand or not. If you do not understand, let me know. I have my glasses to see close, but otherwise everything is fuzzy. Okay? No question? And you want to make sure you see the red dot. Last time I forgot the audio, but now it's working. Okay. So I think we did this one. Slide 13. Okay, let's do this one. So that one comes from a book. If you want to, it's a book. It's a cheap book called Physics Made Easy, something like this, and they have good problems. Okay, so it's a good one. It's interesting one. Okay, go for it. Okay, you can help each other. Like someone sit next to you. I'm not very comfortable. Go fast. Yes, yes. Okay. So first of all, you want to make a drawing. Okay, so you have a little girl. I apologize for the stereotype. Mhm. Okay, and this is 20 kilogram, and she is 35 kilogram. So thing number one and thing number two, and that's before and after. I'm not very good at drawing. After, boom, she's jumping out. Very ugly. So she's jumping. And so that will be the velocity of the little girl here. So that's gonna go back 3.8. And so that's thing number one. So that will be V1 prime. And that will be V2 prime. Okay. So I don't know if you can see what kind of situation do we have? Recoil situation, because before nothing moves. They are together, nothing moves. And then they burp out each other. So it could be a gun and a bullet inside. It could be two ice skaters. You can do if you know how to do if you want to do a demo and you know how to do what's skates, right? You can push each other and see if like if one of you put a weight, like a vest with weight inside, you can see what's going on. Twice, if you make it twice the weight, you should have half the speed. Many experiments you can come with. If you don't have skates, you can do with a skateboard. You can go to Walmart, do your experiment and not buy the skateboards. And even get, if you go to Walmart, you can even get the weights, right? Even the weight in your hand, right? You don't need the waist, the vest. I see those crazy people. They run and they have a vest. Okay, but that's good. I guess exercising is good. Okay, so M1, M2 equals minus V2 prime over V1 prime. Okay, because that's the magic equation for recoil. Otherwise, you can spread out the equation, you will get the same thing. M1 is 35 over 20 equals minus, so V2 prime, oh, I know, is 3.8, and that will be V1 prime. Agree? And it's, it should be, you see here it's minus, so it will be minus, minus. So we have V1 prime equals, you cross multiply, so 20 times 3.8 divided by 35, and you get 2.17, right? And then you check if it's consistent. You expect the little girl to go slower because she has more mass. So it's always the same story. The force is always the same, not the consequence. The acceleration will be larger for the wagon. It goes from 0 to 3.8, and the acceleration will be smaller for the little girl because she goes from 0 to 2, because she has more inertia. So, but the change in momentum will be the same, right? So that means the change in momentum for the little girl will be equals to the change in momentum for the wagon. So the change in momentum is the same, but for the wagon, the momentum goes more into the speed, and little girl, the momentum goes more into the mass. But the exchange in momentum will be the same. The transfer, I think that was one of the questions for test number 2. The transfer of momentum is the same, right? Because the force is the same. Okay. Are we good? So we did the little girl. Okay, let's do maybe this one. Okay, quick. This one. And I think that in Dropbox you can find also a tutorial. Okay, we have to draw. Even in chemistry, yeah, you want to be able to draw stuff. 1.2, ta ta ta, ta ta ta. So this is 12 kilogram. And you have a basketball. So that's before. 1.2. The basketball is going at 7.5. Okay, you want to make sure that plus and minus, don't wait for me. It goes zoom, and it's gonna bounce back. So that's before. I'm gonna call that number 1, thing number 1, thing number 2. And after the basketball is bouncing off, so it's transferring some of its momentum to the wagon. So the wagon gained momentum, and the basketball lost the same amount of momentum. So it was here, it bounced back, and 1.2, and it lost some kinetic energy, 3.8. Okay? It's an elastic collision. And so this one is going this way. So V2 prime, and this is V1 prime. Okay, so try to do it. Okay, here it's easy to make a mistake. Remember that left velocity can be negative because velocity is a vector, right? So we can say momentum before equals momentum after. So don't wait for me. 2.7. What did you get? And who else? Maybe I've done a mistake. I don't know. 0.3, 2.7. Anyone else? Okay, M1 V1 plus M2 V2. Do it. Not just 2 people here. Do it. More you do now, less you have to study for test 3, and you have more time for something else, for chemistry. So you see here, you have 1.2 times 7.5. Okay, this one is dead, 0 equals. So thing number 1, it's bouncing off, but here I have to be careful. What's the velocity? Negative. Okay, plus 12 V prime. And I'm solving for this. You see? So we have to be very careful, because if I don't put a negative sign, when it's going on the other side, it's going to be subtracted instead of being added. Okay? So do the math. 1.2 times 7.5 plus 1.2 times 3.8 equals 12 V2 prime. So what do you get? Huh? Okay. 1.13. That's Gabriela? I know, because the voice comes from, I cannot even see you, but I know it's Gabriela. 1.3 meter per second. Okay, moving to the left. So if you find a negative sign, that means you have done a mistake, because according to the situation here, you expect this one to be positive. Okay? So that's all, it's not that hard. So this unit is easy, really easy. Kinematics, projectile motion is hard. Equilibrium is hard because of the trig. But this unit is not that bad. And you have a lot of application in sport. Like if you're an athlete, momentum. Okay, and you can apply that to many kinds of situations. So I don't know if you recognize this situation here.
No. Yes, it's
Very good, GFK. And so there was a whole discussion, because when they study the body, you had stuff coming from the front and stuff coming from behind. So people thought you must have two shooters, right? Because you have something coming here and something coming there. And then you have a physicist. His name was Luis Alvarez. You can Google his name. He was a genius. He got the Nobel Prize for nuclear physics in physics. So very, very, very smart person. But he said, look, like he could not do it at the time, so he did it a different way. He did that kind of experiment here. If And you can do that with high speed photography. If you shoot something like an apple, right? You shoot an apple, so the bullet goes in this direction. Not only you're gonna have stuff going from the front, but you're also gonna have stuff going from the back. And why is that? Because of conservation of momentum. The total momentum before has to be equal to the total momentum after, and momentum is a vector. So first, the bullet goes really, really fast. It has a small mass, but all the momentum goes into the speed. So very large momentum. It's going into the apple, and the bullet is not going to slow down that much. So it still has a huge momentum, but you also have the stuff here, right, that add up to the momentum of the bullet. So to have conservation, you need something to be in the opposite direction, to have conservation of momentum. Consequently, in that type of situation, not only you're going to have stuff shooting from the back and stuff being projected in the front. So it doesn't mean that you didn't have two shooters, right? It was one argument. It's a very famous argument from Luis Alvarez. That's a very good question. He did. He did prove it, because at the time he didn't have high speed.
mathematically.
No. He did experiment. Let's see. No, I'm not here. So, by the way, that's you see that too, right? So if you have a watermelon and you shoot here, you see you have a bullet, you're gonna have stuff going in this direction and in that direction for conservation of momentum. Uh, I just need to find. I don't know what it's doing here. Unit momentum. I think everything is messed up. My drawing. I have to fix that. Mm. Here, Luis Alvarez. That's how he did it. He took some kind of watermelon, right, a cantaloupe, and he put a duct tape around it. That will be the skull. And then with a rifle, he shoot at it, right, and then he took picture after picture, like all the frame, the frames, different frame, and he was able, thank you, to show that not only stuff was coming from the front, but also in the back. That's how he proved it. But it doesn't prove that you didn't have two shooters. It proves that even if you have one shooter, things can come in opposite direction because of conservation of momentum. So you can Google it. Luis Alvarez and the experiment here. He was a genius, very, very interesting guy. This guy was so interesting that and we are back in the 80s, right? He got the idea to find out, but I'm taking a tangent. He wanted to find out if you have a secret chamber in the Great Pyramid, in Egypt. Mm-hmm. So he got the idea to use particles from space. It's called muons, right? You have muons going through your brain like every second. Muons are ghost particles, so they're not going to do anything to you. But he wanted to use them to highlight the inside of the Great Pyramid. The same way when you are doing a PET scan, for example, you are using gamma rays to highlight the inside. So this is the same idea. But at the time, they didn't have the right technology. However, they did it. They took his idea, Luis Alvarez, in 2017, and they did find something here, but there was nothing inside. But they saw that you had like some space inside. Luis Alvarez, really, really interesting character. I had more picture to show you, but I don't know. It seems that I'm missing the inside of my folder. Luis Alvarez here. Okay, Luis Alvarez, right? It happened in early 70s, 60s. He already had the Nobel Prize and the Warren Commission that they were investigating the assassination. So I don't know. You can go back to my video and look at what it says. But very interesting. So anyway, this is because of conservation of momentum. Momentum is a vector. Okay, so here is an idea for a demo for you. Well, because of conservation of momentum, let's say you are on a skateboard, okay, or something that can roll, and you have a bag, a tennis ball, or ping pong. No, ping pong won't work. Or golf balls, or tennis ball, right? And you throw them like this. What's gonna happen? You go back, very good, you go back because of conservation of momentum. Before you are not moving, you throw this one forward, the whole system has to move backward. So it's like you are pushing yourself and the skateboard on the tennis ball. So you're gonna move back. So this is how a rocket works, and that's how you can find the equation for a rocket, how it works, right? So you are burning fuel, the rocket is pushing on the exhaust gas, so the exhaust gas is pushing back on the rocket. Okay, the acceleration will not be the same, but uh, the force is the same, and the acceleration depends on how fast you are burning the fuel. So imagine you have a bag, like a bag around you, and you put a lot of tennis ball. You're standing on a skateboard, right? You need a lot of balance, and you go this, and you should see that you're gonna move faster and faster and faster. And you can, I mean, if you do it at the same rate, your speed should increase, but the acceleration should be the same. Okay, so you should see that you're gonna move faster back, but your acceleration should be the same. So it depends how fast you are burning your fuel if the tennis balls are the fuel. Isn't that interesting? Depends on your mass as well. It depends inertia, right? Okay. What's gonna happen here? Which way you're gonna move? So now the ball is bouncing back. So which way you're gonna move? Yes, so forward. Okay, so if you are very handy, you can have a skateboard, and then I don't know how you will do that, but you attach some kind of sail, and you throw tennis ball at your sail, and you're gonna move forward instead of backward. Exactly. So you can do that with a sailboat. No, no, that will not be a good idea. Yes. So you will move forward, and the thing will bounce back. Now, if you catch it, what's gonna happen? Instead of letting go, you catch it. Very good. You're not going anywhere, right? You're gonna just feel something like this. Isn't that cool? That's why people don't like physics, because if you do not do the experiment, you cannot appreciate. It's boring. But if you do the experiment, wow, something else. So much better than chemistry. Okay, so that will be conservation of momentum. You also have conservation of spin. Okay, so we're gonna get into rotation. So the same principles will apply to rotation. So it's very easy to understand conservation of speed. Here's another demo. If you're a good ice skater, it's hard in Miami, I guess, but if you spin, right? So you spin, what's gonna happen if you bring the arms in? You spin faster. Very good. And this is because you have conservation of spin. When you bring the arms in, you decrease your inertia, so you're going to increase your speed. So this is conservation of speed. Yeah, new unit, torque. Okay, torque. Okay, so torque, very important for students who are going to go into exercise science, physical therapy. Now you can be a doctor, you can go to graduate school and be in physical therapy. It's a lot of jobs, because all those people on their computer, as they age, it goes like this, like this, like this. So there is a lot of fixing to do. So you will never be out of job if you go into physical therapy or exercise science. And why do I say that? Because we're going to talk about levers, and the whole human body is about levers. Everywhere here, the mechanical system inside the human body is going to be about levers, right? So it's a special discipline called biomechanics. And at FIU, I heard, so I don't know if he's still teaching, but there was a professor who was teaching biomechanics. I don't know if you know him. And he was the coach of the Patriot of what's his name? Brady, Tim Brady? No, Tom Brady. Tom Brady, thank you. So he is very good. Biomechanics. So about torque. So you have two kinds of motion. You can have translation, and you have rotation, or you have translation and rotation. Okay, so if you want something to rotate, the new physical quantity that I'm going to introduce, it's called the torque. A torque is like a twisting force. It's what making the rotation happens. Either it's going to spin faster, either it's going to spin slower, or the orientation of the spin is going to change. So that new physical quantity, you can call that like a twisting force. It's called the torque. And you can think of that as a way to measure how efficient a force is in applying a twist. So let me explain. So you have a door. Can you see the door here? You look at it from above. Do you agree? Are you with me? Okay. And you want to have a twist here, a rotation about the axis of rotation. So you always have an axis of rotation. sometimes it's called the fulcrum. So this is the axis of rotation, and you want the door to rotate. So of course you want to apply a force, but that's not the only thing that is important here. If you apply the torque this way, is it going to happen? Are you going to open the door? No. What's going to be the direction the most efficient you want to have? Perpendicular. Okay, so that's going to be here. That's the distance here between the point of application of the force and the axis of rotation. To be the largest torque, the most efficient, to be the most efficient, you need to apply the force perpendicular. Agree? So the direction matters. The force matters, of course. If you are giving a big push or a small push, what else matters? Exactly where you push. Is it harder to push here or is it harder to push there? Closer to the axis of rotation, it's going to be harder, right? There is a reason why the doorknob are very far away from the axis of rotation. Farther away, easier it's going to get. So we need to take in account when we're going to define the torque, we need to take three things in account. We need to take in account the force, very good, the magnitude of the force, and then the direction, very good. Who said that? Very good. Daniela. But because you are in costume, so now imagine you in the costume. Daniela. Yes, the direction and also the distance. Very good. Yes. So three things. Okay. And so in that situation, it's very simple. If you want to find the torque, so in physics, when you have three things to take in account, you just multiply them. Sometimes you have exponents, sometimes you divide. But in that case, very simple. To find the torque, you just multiply the force by the distance between where the force is applied and the axis of rotation. That's all. So the unit will be Newton meters. And the torque is a Greek symbol and it's tau. Okay, it's like a tau. It's a tau. It's a Greek letter. Example, if the force is 50 Newton and the distance of the range is 24 centimeter, the first thing you have to convert centimeter. What's so funny over there? She's laughing. So 24 centimeter to meter, what is it? She's on her trip. 0.24. So 0.24 times 50, 12. Okay, 12 Newton meters. That's going to be the torque. You see? Isn't that easy? Right? So typical situation, I did a video, but I don't know if it's there. Torque. Me. It's me. No, it's my sister because I don't look good here. Okay, so it's me. So this is the axis of rotation. And if you want the wheel to spin, you need to apply a torque, right? And the force has to be perpendicular to the radius, right? So the distance between the axis of rotation and the point of application of the force, right? So the force will be in this direction. That will be your distance, right? And you see, my son is going to apply a torque. and it's going to spin faster, and you can apply a force to slow it down, slow it down, slow it down.
The vector will be in that direction.
Okay, so what I'm saying here is turns out that the torque is also a vector. So if the torque makes the object rotate in this direction, the torque will be the vector will be this way. Okay, you take your hand, you have a thumb. If it's spinning this way, that will be your torque. So torque is also a vector. So we are not going to worry about that too much. You see, I was very tired.
That will be the vector torque. Also, the
It's gonna
angular
slow down.
momentum, okay, which is also a vector, will be this way. So a torque can make a
Slow down. So you see, you apply a torque to slow it down. That way I don't have to carry the wheel because it's in my office. So if you come up with an experiment, you can borrow it, but it's a bit it's a little bit heavier. So what do you think? The top one is easier, right?
Mm-hmm.
So if you're doing things at home, like work, if you're handy, longer is the range, easier it will get. So it's like a force multiplier. It will get easier, but there is always a price to pay. You have to do this and this and this for that to move a tiny bit. So for the same force, if the distance is divided by 2, the torque is divided by 2 as well. Okay? So what do you think? Do you all agree? A, B, or C? So C will be easier. So that's what we call a lever of type 1. It's a machine that makes you stronger. It's like a force multiplier. And Archimedes said, give me a lever and I can lift the world. Turns out, if that distance here is 3 times that distance, it makes you 3 times stronger. So if you have like 30 pounds to lift, 30 pounds is not that much, right? But if you have 300 pounds to lift, you cannot do it. You use this machine, and if this distance is 3 times that distance, you can only push with well, very good, 100. What's your name again? Ethan. Yes, 100, right? Do you agree? Yes. So there is always a trade-off between the distance and the force. So the price to pay is that if you push 3 yards, that will be lifted only 1 yard. It's a machine. So always a trade-off between the force and the distance, or the force and the speed. It's like high gear or low gear, right? Okay, so here let's get a little bit more complicated. So C, what's the torque produced by the force C? Is zero. Very good. What's your name? Gabby. Okay, force. Yes, the torque will be zero because there is no twist happening. It's very inefficient. What's the most efficient between A and B? It has to be perpendicular. So which one is perpendicular? A. So B, guess what? We come back to vectors. The vector B has 2 components. One component here is not helping at all. It's just pushing the stick into the ground. And why only one component is doing the work. But I will not, this unit will be easy. I'm not going to make it too complicated. Okay? So that's really the definition. The torque is the distance between the axis of rotation and where you are applying the force times the perpendicular component of the force. Does it make sense? Remember that a force is a vector. It has 2 components. So how do we find the components? This is the tail, that will be the origin. The head is showing you the XY. Okay, so you go from the tail to the head. That will be the perpendicular one, that will be the parallel. Or that will be the parallel, that will be the perpendicular. Do you understand? So this component, what it's doing is just pulling away. So it doesn't help with the twist. Only this component is really helping with the twist. So the real definition of torque will be distance times the perpendicular component. Agree? And then a torque can be positive or negative just by convention. If the twist wants to be clockwise, it's going to be negative. And if it wants to be counterclockwise, the torque is positive. It's just like convention. Okay? So, again, if you need to review, it's you cannot memorize cosine or sine. It depends. You need to make your right angle triangle. So if this angle here is given, that will be called the adjacent. So you use cosine. This one is opposite. So that will be the sine. And that will be the hypotenuse. Okay, so just a review. Example, let's try to do this one. So why don't you try to find the torque produced by the force F, and then that force F here has a magnitude of 100 Newton. You see it has two components. You see you have your parallelogram, you go from the tail to the head, and only the perpendicular component is doing the work. And then you just use basic trick. Okay, and you don't stare, you do it. So this is 40 degrees. That's the issue. After 1 hour, students space out. Don't space out yet. Okay, so the magnitude here is 100 Newton. So this is your force. It has two components. You see, I go from the tail to the head. This component is pushing the stick here into the ground, so not very helpful. It's only this component that is doing the work. So the torque done by the force F, or produced by the force F, relative to this axis of rotation. So that's my axis of rotation here. It's like a fulcrum. So the torque produced by F about this axis of rotation equals, so it's going to be perpendicular, right, times the distance, right? The distance is 10. So, I don't know, I didn't compute. What did you say? 643? Do you get 643? So first of all, do we use cosine or sine? This side is cosine, cosine. Look, this one, this one. We want the perpendicular one, right? 766. So, okay, so it's going to be 100 cosine 40 times the distance between the fulcrum and the application point, which is 10. And he wants to make it what? Clockwise or counterclockwise? So it's going to be negative. I'm going to put a negative sign. So how much is that? 766 Newton meters. Do you all agree? Uh, so there is no really y or x. we rather say perpendicular and parallel. And parallel to what? Parallel to the distance between the application of the force, the point where you are applying the force, and the axis of rotation. Okay, so it's not really x and y anymore. That's a good question. It's more perpendicular. That's one that is doing the work, and parallel. So in the human body, everything, all the joints, okay, the muscles will be the force, the joint will be the fulcrum, and the load will be for example, a dumbbell, or it could be your own body, your mass. That's why it's so easy to injure yourself. That's why I think physical therapy is a great job. So anyway, any question? Okay, so that will be the definition of torque. So do you agree that farther away from the axis of rotation, easier it's gonna be to be a twist, right? Yeah. So I had a student like long time ago, and he got this idea for a video for extra credit because he was an athlete. Obviously, you're gonna see that he was an athlete, and he did that demonstration. So that's the proper use of the machine. You have the axis of rotation, and on the other side, you're going to have the load. Do you understand? But now look what he's doing. He gets closer to the fulcrum, and he cannot even move it. See? That's easy. Okay? The torque is large, and here the torque is small because the distance, and he's doing push-up at the same time. Or not push-up, pull-up, right? It's pull-up. So I was very happy with that demo. I thought it was a very smart demo. So if you hit the gym, you have all kind of torture instruments you can use for the physics. It's very important to understand how torques work because, for example, here, okay, no problem because here, that will imagine this is your pivot point. So this is going through the pivot point, so there is no torque. Do you agree? Okay, so the load that you have here, okay, there will be the weight, and the weight is going through the fulcrum. So there is no torque. However, as you age or we age, okay, we don't work out enough. So gravity is winning, so we go down, down, down like this, right? We go forward. So to balance out, your muscles in the back is trying to pull you back. So that's why you have back pain, right? So this is your axis of rotation. Gravity is pulling you in this direction. So your muscles in the back have to pull you, try to do this, right? And it's always under stress. So it's very important to understand how it works. So that will be the proper definition of torque. Any question? So for example, in that case, what is the torque produced by the pull here? Nothing will happen. The component is only parallel. So you take the distance between the axis of rotation and the point of application of the force. You pull here, it's only parallel, nothing's going to happen. In that case, yes, it's going to happen. But you see the force here is not perpendicular. So you see, only the perpendicular force is making the twist happen. And if you are given this angle, that will be what? Sine or cosine? Sine. Okay? Remember trigonometry? You take the right angle triangle relative to this angle, that will be the opposite. Agree? For example, here, what do I do? What do I do to find the torque? In that case, you just do right. So it will be the radius times the force. That's it. It's already perpendicular. But in that case, which one is perpendicular? The sine or the cosine? The sine, the sine, the sine. Do you agree? Well, you want me to make a drawing, you see? Okay, so force. And it's very important if you go to biomechanics, things like this, you have to understand that, right? So that will be the parallel. Even if you go to medicine, like some people, they will complain about back pain a lot, so you understand what's going on. If you're an understanding of our mechanical system, so only the perpendicular one. And perpendicular one in that case will be the sine. Okay, so the torque will be F1 in magnitude times sine 50 times the radius. And then he wants to make it go counterclockwise, so it's going to be positive. Agree? Okay, so this I don't know. I thought it was a coffee machine. I think it's like a water pump.
Yeah.
It's old technology. Okay, I'm going to give you a few minutes, like talk to each other and discuss how can you find the torque in each case. And it comes from a biomechanics class, so sometimes I find good stuff. Okay, don't say anything. Just write down. So remember, you need to convert centimeters to meters. Yeah, I don't see what's going on here actually. Here was 13 degrees, oh, 30 degrees here. So the first one is easy. What do you do? What times what? So this is the axis of rotation, okay? And you are pushing down. So you multiply what by what? Yes, 0.5 times 20. Easy, right? So in that case, you multiply what by what? 40 times 0.25, which is 10 Newton meters. And if I want to do the sign, so you want to do clockwise, so the torque will be minus 10 Newton meters, right? So this one, it has two components. Again, remember the origin is at the tail. This is showing you the x and y. So this is the parallel component, and that will be the perpendicular component. So you have your right angle triangle, so it's going to be the
Sine.
sine. Very good. Okay, so you will do 80 sine 60 times 0.25, and with a minus, because it wants to make a clockwise. They all want to make clockwise, obviously, because you are going down. I don't think you can go up. Same thing here, it's 30 degrees. So it's going to be 0.25. And then it's 80. And it's going to be sine 30. Agree? What's going to be the torque here? Is it being efficient in making the twist? No, so the torque is 0. Okay? Okay, that's easy or what? So here, that's the axis of rotation. You can think that there is like a stick into it, right? And you want to rotate. Which force will be the most efficient? Don't say anything. Think about it. Which force will be the most efficient at spinning the piece of wood about the axis here? So what do you think? 3, do you all agree? Okay, we want the force to be as far as possible and not being parallel, so perpendicular or some perpendicular component is good. Is 2 good? No. So the torque, you see, when the force, when you extend the force and the force goes through the point here, that the torque will be equals to 0. So the most efficient will be number 3. Agree? So even though they all have the same magnitude, so it's the same force in magnitude, but it's not the same torque. So a torque is not a force, it's like a twisting force. Okay? So in that case, so for example, if the axis of rotation is 0, okay, think about it. Everyone think. More you think now, less you think at after. I mean, for the test number 3, don't space out. So what will be the torque? What's the force here? 8. And what's the distance? 5. Okay, they try to trick you. You might think, oh, it's going to be 3. No, 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 no. The axis of rotation is here. So it will be 8 times 5, which is 40. Yeah, Newton meters. And this one, we are using the sine or the cosine. Sine, very good. So 12 sine 30 times 2. 12 times sine, okay, 6 times 2, yes, 12 Newton meters. Agree? Okay, let's try to do this one. I'm helping you because you see this is 55, this is 55 degrees, this is 55, this is 55. So that's a tangent. Yes, that's a tangent. No, 55 is the angle. This angle here is 55, so that angle here will be 55 because of geometry. See, this is perpendicular. And this is perpendicular. So between here and there, you have the vertical, that will be 55 degrees. And the force is 790. And what's happening here? You are lifting yourself up. It's a lever. You know, this lever here, when you are doing this on your toes, you are amplifying your force because I'm like 170 pounds or something, and I am able to lift myself just with a few muscles here. This is because it's a force amplifier. It's a lever, right? Type 1. The body is amazing. It's an amazing design. I'm sure you can make more money as a trainer than the physics professor. And you will be in better shape. So this is 55 degrees. Okay. And okay, so 3.6 times 10 to the negative 2 meters, so 3.6 centimeters. But you keep this way. And that's going to be your fulcrum, so the axis of rotation. That will be the force here. And you see the force has two components. It has components here, which is perpendicular Okay, so I have to be careful. And it has a force here which is parallel, and we don't care, right? Okay, and the force is 790. Thank you. 790 Newton. 790 Newton, and this is 55 degrees. So remember, trigonometry. You have a right angle triangle, and you want to find the perpendicular. So the torque is the perpendicular component times the distance between the axis of rotation and the place where you apply the force. Isn't that interesting? Mm-hmm. And the force is from the muscle. And the muscle is attached to the bone by tendon, the famous Achilles tendon. So if you get that will be very bad. So am I using cosine or sine? Cosine, very good. You all agree? Yeah. Right? In a right angle triangle, this is the adjacent. So the torque will be, 790 cosine 55. Yes, so 3.6 times 10 to the negative 2. Agree? Mm-hmm. Yes. Yes. Oh, because it's given to you. The tendon exerts a force of. Oh yeah. By the way, you know what a tendon is? Is like it's transmit the force. So do you remember the tension when you have a rope and the force will be the same all over? So the job of a tendon is to transmit the force. It's like a small rope here. So whatever it's pulling here, it's gonna pull there. T and T. Isn't that interesting? And you can train your tendon to be more flexible. So anyway, so what do we get? 163. Okay. No, not 163. Because here it says 790 and here it's 720, so there was a mistake.
16.3.
So how much is that? 16.3. Okay, 16.3 Newton meters. So here it's 3.6 times 10 to the negative 2. So you want to keep it in meters, right? Which is 360 centimeters. No. 36 millimeters. Yes, 36 millimeters. But you want the distance in meters. So 16.3 Newton meters. Do you all agree? Mm-hmm. Okay, over there. Okay, except here there is a mistake. I don't know. It comes from your book, Johnson and Catlett, by the way. It's very good for biology. Okay, that's why we have to be careful. So why, for example, like if you have knees like this, right? It's easier to have like a meniscus issue or the meniscus to rip off because you see you have the axis of rotation here, and then if it can apply a force here, whereas here it's going to be more stable. That's why women tend to have more issues with their knees. I experience talking because women have larger hip, so you see it's easier to damage, to have some issues with the knees, right? Here, is it easier if you have a longer or short arm?
Maybe a short arm.
So
Oh no, longer.
longer. if you have longer arm, it's going to be easier because this is your axis of rotation. That will be where the force is applied. So those with longer arm have an advantage in that competition. Okay, I don't know, shall we do something easy here? It's all very easy. Okay, let's do number 3. Just for fun. Do it. Don't stare. Don't fall asleep. Wake up. Okay. Steering wheel. So you have a wheel. I don't know, it looks like, I don't know what it is. It's supposed to be a wheel. And you apply a force. So the force is perpendicular here. And it's supposed to be perpendicular. It's not perpendicular. Okay, forget about my drawings. Just do it. So 150, let's see. So torque equals perpendicular force times the distance. So this is 30 equals the force times the distance is 0.26. So the force equals 115. 115? Mm-hmm. Do you agree? Mm-hmm. And so this is the rate. I don't know how to draw, okay? So that's the force. Any question? A lot of application in sport. So there is a saying, low man wins, right? So it's easier to topple someone from the top than from the bottom because that distance will be larger. So there is all physics about sport. So let's talk about levers. So that's the thing I want you to remember. You always have a load, you have the fulcrum, and you have the effort. If you want to have the effort farther away from the fulcrum than the load. Does it make sense? You see, when we go back to here, you want, this is the load, this is your fulcrum, that's the effort. If you want the lever to be a force multiplier, you want to have the effort as far as possible from the fulcrum. You want the distance between the effort and the fulcrum larger than the distance between the fulcrum and the load. Does it make sense? So typical example, you have a crowbar here. The effort will be farther away from the fulcrum than the load. Okay? So you have different types of levers, right? For those going into biomedical exercise science, you have type 1. So this is a type 1 lever. That's when the fulcrum is between the load and the force. In that case, you can use that as a force multiplier or as a distance multiplier. If the force is farther away than the load, it's a force multiplier. Otherwise, it's a distance multiplier. Okay, so that will be an example here. You see your head, that's the axis of rotation. You have a muscle there, and that will be your load. And then you have the lever type 2. This is always a force multiplier. Push up. This is the axis of rotation. That will be your effort, and that will be your load. You see the effort is farther away from the fulcrum than the load is. So this is a force multiplier. You are able to lift yourself, okay? But it's a way to cheat, quote unquote, okay? Because it's a force multiplier. In that case, that will be class 2. So for example, in that case here also is a force multiplier. Agree? But the example we always give is this one. When you lift your body up, your load will be your whole weight, 160 pounds down to earth. And just with these little muscles here, not much, you are able to lift your weight. How it is? Because you are using a force multiplier. The only thing is that it's not going to be lifted very, very much here. You see how it works? So this can be used both ways. Force multiplier, distance multiplier, level 2, force multiplier, level 3, always a distance multiplier. So if you are doing this with your arm, that will be the load that you have in your hand, the dumbbell. Okay, you have a dumbbell in your hand. This is the axis of rotation here, your elbow. And the muscle is attached somewhere there. It's doing this. And the effort is very close to the fulcrum. So it's not making you stronger, but it's going to amplify the distance. So that's why it's you don't have much force in this here, right? Because it's not meant to lift heavy weight. You amplify the distance, but you don't amplify the weight. So this is level 1. Okay, so this is bicep extension. So I guess you are doing this, right? So this is also a distance amplifier. So if you are interested, you can take the time to look into it. Super interesting. And then you can understand why your back hurts, your knees and things like this. You don't have to worry yet because you are young. But will come a time you will get back to your slides and you will say, oh, okay, now I understand why. All these are amplifying the distance. Okay, so here you are pulling here. Okay, this is the fulcrum, and here you have a large distance. So you can amplify the distance or amplify the force. Same thing, so this is called deadlift. And you see, this is the right position for deadlift. This is the axis of rotation. Here, the axis of rotation is there. Okay, this is your load. The load is down. The axis of rotation, the force. Okay, and this is a distance amplifier. And the force applied will be in the glut, in the glut here, right? The force will be there. Okay, so all here, it's working like levels. So that will be a domain. It's the discipline is called biomechanics. You have pulleys also there. Okay, wheel and axle. So super interesting. Okay, and we go back to equilibrium. So just an introduction. If this is an equilibrium, what will be the equation that you can come up with? So that will be weight 1, distance 1, weight 2, distance 2. If you want an equilibrium, you want the torques to be the same, right? The torque that will make it clockwise equals to the torque that makes it counterclockwise. So what's the torque here on that side? Will be F2 times D2, right? So distance 2 times F2. Agree? What will be the torque on the other side? F1 times D1, right? And they want to be equal to each other. Does it make sense? So when my kids were long time ago, we were playing seesaw. So I will put, like, let's say I am 300 pounds and my kid was 100 pounds. So I will come closer, sit close to the fulcrum, and this ratio here is exactly 3 to 1. Then you will have equilibrium and you will have fun. Because otherwise, if you sit there, the kid is always up, it's gonna get tired, right? Here is another demo you can do. If you have a nephew or a niece, you can try. You can find the exact spot coming closer to the fulcrum where you're gonna be both in equilibrium, and then you can find the ratio between the distances, the ratio between your weight, and it should be the same. Great demo. With quantitative method, you find the ratio between the weight, and it should be equals to the ratio between the distances if you are in equilibrium. That's how I used to do seesaw with my kids, except it hurts, of course, to sit there. Okay.